Hello, everybody. So I hope you had a nice weekend and a chance to look at the homework. Today, I'm going to talk about a couple stuff. The first one is to talk more in detail about the appendix that I uploaded last week after office hours, related to one of the last calculations of lecture one regarding convolution. And the other part is going to be the continuation of time-independent perturbation theory. So let me share the screen. And let's start. Okay, so first things first, the appendix. So I wanted to explain in more detail one of the reasons of the last calculations in the lecture one, which is related to the Schrodinger equation in the momentum representation. And I simply want to explain or justify why this equality holds, which is that the Fourier transform of the product of B with psi is equal to this expression. And actually, this expression is or can be understood as something called convolution. And the convolution is a property that appears in Fourier transforms of products. And it's quite important. If you studied Fourier transforms in your mathematical physics course, you probably saw this. And there's a theorem, again, in Fourier transforms of products, which is called convolution. Let's start by defining convolution, which is the following. The convolution of two functions is defined as f convolved with g is equal to the integral over the real line for 1D functions of g of y times f of x minus y dy. So notice, first of all, the integration variable is y, which is the argument of g. And f is kind of like traveling the real line in the opposite sense. Instead of going, say, to the right, it's going to the left, but with this shift related to x. One of the properties of convolution is that it's commutative. So f convolved with g is equal to g convolved with f. It can be proved. And under the following definition of the Fourier transform, which has a different normalization factor, we actually have the 2 pi factor here, and we don't have this 1 over the square root of 2 pi. And actually, you might have noticed that in the other, or in the definition of Fourier transform that we use for our course, we had the h bar factor involved in there. But okay, under this slightly different definition of the Fourier transform with different normalization factors, there is the following theorem stating that the Fourier transform of a product is equal to the convolution of the Fourier transforms of the respective functions. So Fourier of f times g is equal to Fourier transform of f in convolution with Fourier transform of g. If you simply write the definition, so this is an important theorem that you probably saw in mathematical physics. If not, I'll give you some references at the end. But by definition, the Fourier transform of this product is precisely right. So you have the Fourier transform operator in this definition that we had before of f times g. Here you would have the convolution on the other side. So the convolution of Fourier transform of g with the integration variable k prime, and then convolution or in convolution with the Fourier transform of f, which has the argument k minus k prime integrating over the k prime. So if I expand a little bit more this by definition, I'll simply get that, okay, the Fourier transform of g is over here with the argument k prime, so Fourier transform of g. And then I will have the Fourier transform of f with the frequency k minus k prime, which is precisely what I have on this side, under this definition of the Fourier transform, right? So I'm just applying definition. And again, this is quite usual in an either partial differential equations course or a mathematical physics course when you touch the topic of Fourier transforms. If you have not seen it, I'll give you 2 references at the end where you can look on more info. And with this knowledge, we'll use the theorem under the different definition of Fourier transform that we have to justify our equality. yeah, again, notice this is the definition of the Fourier transform that we used in our notes for lecture 1. So we don't have the factor of 2 pi. And we have this factor of 1 over square root of 2 pi h bar. And we have the Fourier transform of a product nevertheless. Under this different normalization of the definition of the Fourier transform, we need an extra factor of 1 over square root of 2 pi h bar in our convolution theorem for products of, well, for Fourier transforms of products of functions. And here we would have the Fourier transform of B convoluted or convolved with the Fourier transform of psi. Now, we know that the convolution is commutative, so we can put simply psi first and then the potential in terms of these Fourier transforms. If we do that, and of course, remembering we have this extra factor, so applying that definition, I would have in the convolution, remember, the Fourier transform of the other function integrated in the integration variable frequency, which is p prime, times the Fourier transform of the other function, which would be psi, integrated, well, also with respect to this variable, but it's the Fourier transform is related to the frequency p minus p prime, which is over here. So far, so good. Now, at this point, I can do a couple stuff because here what I'm having is precisely the Fourier transform of psi, the wave function in position space, related to the frequency p minus p prime. That, by definition, is going to be precisely phi of p minus p prime. So that's the wave function in the momentum representation. So that explains this factor, okay? Then I'm just rearranging things in different order of integration to apply some sort of Fubini theorem in order to justify what I have below. So this is the integration variable, of course. I will have the Fourier transform of the potential in the frequency p prime. And here I have again the Fourier transform of psi, but with frequency p minus p prime, which explains why I have phi, the wave function in the momentum representation, evaluated at p minus p prime. And then I have the Fourier transform of the potential, okay? And then I integrate over p prime with my extra factor. So this is the explanation of why that equality holds, where I have just used two properties, essentially the convolution theorem for Fourier transforms of products and the commutative property of convolutions. And that's it. So it's just nicer to express in this way this term in the Schrodinger equation in the momentum space. And of course, again, I stress that I have the Fourier transform of the potential in this part. Of course, this other term that I already recognized. And yeah, just be mindful of these two properties. If you have not seen this before in your mathematical physics courses or a partial differential equations course, the three references I could recommend you are the book by Arfken in Mathematical Methods for Physicists, which is a very famous book for mathematical physics courses. You may have used it. If not, it's quite a good reference. It's actually pretty standard. Also, well, an online resource if you want to see in more graphical fashion the convolution theorem and its consequences, which is related to Math World, Wolfram Web resource in this direction. And the third reference is basically the book in quantum mechanics, where it is explained in more detail the Schrodinger equation in the momentum representation. Actually, I follow part of its approach in this calculation. You may have noticed that I reference it on the lecture. So hopefully that will help in the clarification of this calculation. And if you have not seen this before regarding convolution, I would recommend you to at least take a look at it and read it, because it's quite important, especially in quantum mechanics. Okay, so I'm going to continue with time-independent perturbation theory. And in this part, I'm going to focus on the second order corrections to energy levels that are not degenerate, okay? So, well, The theory is somehow short. I want to present an example in detail, though, that presents or that shows many um, of the issues involved with perturbation theory. With a simple example, relatively, in the sense of its posing, perhaps not so much in the solution, but yeah, I think it gives a good flavor of what is happening. In any case, so let's continue with time-independent perturbation theory and second-order corrections to non-degenerate energy levels. So if we focus on the second-order equation for the respective corrections to energies and states, basically this is the equation that arises in the second order in lambda powers. So when I collect terms of order lambda squared, or power 2, this is what I would have. On the left-hand side, of course, the original Hamiltonian, evaluated on psi 2n. Here, for h prime, psi 1n appears because remember that the perturbation had a power in lambda, so that's why I have a reduced order in this part. And then I will have the three terms which are related to the products of the corrections in the energies times the corrections in the wave functions. That's why I have like this matching of the powers where I have E0n with psi 2n, E1n with psi 1n, E2n with psi 0n, right? So there's a balance, and these are the terms that are related to lambda squared. So we'll do something similar to what we did for first order. We'll take inner product of this equation with respect to the unperturbed wave function psi 0n. So basically, when I do that, I would have, well, basically these two terms. This one is easy to carry out because let's take inner product, which is each one of these three terms, right? So, well, I can take the E0n factor out, and I have product of psi 0n with psi 2n. Then, excuse me, I would have E1n coming out, and then inner product of psi 0n with psi 1n. And then E2n of psi 0n with itself, which is 1. And actually, in the unperturbed basis, I have orthonormality properties, which are going to make some of, well, some of the terms basically 1, as in this case. And so we have to remember what each one of these terms involves, right? So of course, this is the wave function for the unperturbed Hamiltonian. This is basically related to the, how can I say, the first order correction, and this is related to the second order correction to the wave function. Now, actually some terms might be eliminated, and so that's what's interesting, right? So, okay, if I study more in detail this term, I have some linearity property, which I use. I also know that, well, this matrix is Hermitian, so I can pass it to the other side, and I have unperturbed Hamiltonian applied over psi 0n. So, okay, having these two terms, this will make an energy E0n pop out, as I have it in this fashion. This term remains the same. And so this is nice because, well, actually I have this same term on each one of the two sides. At this point, I have no knowledge of what psi 2n is, because that is the second order correction to the wave functions, and so far I haven't calculated. If you remember, I did the calculation for the first order correction to the wave function. So it's convenient that it disappears, and I still have this term. I will pass it to the other side, and if I eliminate and pass, I have this. So the second order corrections to the energies is basically this matrix element, or actually not exactly a matrix element because I need to substitute psi 1n for the expression that I have. Sorry about that. And then I have minus E1n of inner product of psi 0n with psi 1n. So again, I'm going to need the relation that I found before for the first order correction to the wave function. So, and this was done in terms of the complete set of the unperturbed eigenproblem. So the relation that we found last lecture was precisely this one, right? Is the sum over all states different to n, where I have this matrix element. Now it's indeed a matrix element related to the unperturbed wave functions times psi 0n, and then with this, or divided by this difference in the energies, which is the main reason for which we are sticking with the assumption of unperturbed energy, so that this term doesn't become zero and blows up the whole thing. So, well, again, as we justified last time by some sort of Gram-Schmidt procedure, psi 1n has no psi 0n component. So actually, when you do this inner product, one of these terms is going to vanish, actually this one. So if you were to do that, knowing that this term is going to become zero, precisely because you're considering all states different to n, you have the second order correction is psi 0n with h prime psi 1n. So you have to plug in again this expression. So, okay, if you do that, you can use linearity properties, which will take out the sum. Then you have on one hand this term that appeared in here, and then sandwich with this other one, which is actually its complex conjugate, because here you have mn and here you have nm. And so basically by properties of the matrices, you'll have the norm squared because it's a number multiplied by its conjugate. And then the second order correction is the sum over all levels different to the one that you're correcting to, or with respect to, of this matrix element squared with respect to h prime, divided by the difference of the energy level C0 and minus C0. So again, having non-degenerate energy levels is quite important, because if not, this would blow up. And yeah, I mean, there are kind of like several important points to discuss, but the main one, or the moral in a way, is that usually it's enough in quantum problems to stop at the second order correction to the energy and at the first order in the wave functions. Very rarely you need more. There is more info into why that happens. I am holding a little bit in explain it because it's like a twofold issue. But okay, the theory was short, right? It was basically follow up with the calculation of matching powers, rearranging terms, recognizing which ones were zero, noticing that you have the conjugate, and then you're good. And okay, this is nice. You have basically a real number in here, which should be for the energies. And so we're going to do a problem where some of the issues that I have mentioned before will appear. So let's do one example of application of second order non-degenerate perturbation theory. So I chose a problem of Griffith's, which I think it's interesting, both for the physical and the mathematical consequences of what is studied in the problem. And so it goes like this. Let's apply perturbation theory to the most general two-level system. So basically, there are only two possible energy levels, which are not degenerate. So the unperturbed Hamiltonian, of course, is diagonal in this two-level representation with each one of the energies. So those are the eigenvalues. And the perturbation, again, is going to be the form lambda h prime, which is lambda, okay, matrix that is not necessarily diagonal, of course, because it's the most general case for two-level energies. And the conjugacy has to hold because you are working with a Hermitian matrix. So, I mean, of course, the diagonal terms have to be real. Yeah, that's because it's Hermitian. And lambda is a constant later to be set to 1, which is what we usually do in perturbation theory. We use lambda to keep track of the order, but at the end of the day, we ignore it because it's the case lambda equal to 1 that we care. So, okay, find exact energies to this two-level energy system. Well, we have to pose the problem in the way we have learned, right? So, okay, first of all, what is the full Hamiltonian? The full Hamiltonian is h naught plus lambda h prime. So this is the sum of the diagonal matrix with the lambda term times the h prime, which has this fashion, of course. The non-diagonal terms are related to the perturbation, as we know. And we want to find the exact energy. So for a 2x2 matrix, basically you have to find the eigenvalues, which is something that you're familiar with from your ODEs course. So the eigenvalues, which I'm going to call mu in this case to distinguish from the lambda, which is a parameter for the perturbation. So the eigenvalue equation, of course, is the determinant of the matrix minus mu, the identity, equal to 0. And I have the characteristic polynomial, which of course I can express in two different fashions. The first one is, of course, by basically computing the determinant directly of h minus mu I, which is over here. So notice the mu appearing in this part. The other is, again, you probably saw this in your ODs course. For a 2x2 matrix, you can express the characteristic polynomial as mu squared minus trace of h times mu plus determinant of h. So those are properties that are quite useful in the 2x2 system. So this is just because perhaps it's a little bit simpler to express it right away instead of doing this computation as a quadratic equation. So the trace of h is, of course, this. So EA plus lambda BA plus E0B plus lambda BBB. So that's the trace of h. Okay, minus trace times mu plus the determinant of h. So if I were to compute the determinant, I have E0A plus lambda BAA times E0B plus lambda BBB minus lambda squared. And basically, yeah, these are conjugates of each other, right? So that's why I have norm of BAB squared. So at this point, this is in the fashion of the quadratic equation where I can apply the well-known formula. So that's why I have minus this term over here for the solutions plus minus square root of this term squared minus 4 times 1 times my sort of C, which is this one, which is what is appearing in here, divided by 2 times 1. So I can do some simplification just by noticing that actually, look, I mean, if I were to expand this by taking the square, I would have the square of this plus the square of this plus the double product of this times this. And here I have minus 4 times actually the double product of this times this. So if I incorporate or basically add the full expansion of this quadratic term with the minus 4, this stuff, I will have minus the double product. And so I can actually factorize that as the difference squared. So that's why I will have E0A minus E0B plus lambda BAA minus BBB squared. So that's taking charge of this term. And I just simply have the plus 4 lambda squared BAB squared norm. So far so good. It's a little rearrangement, but formally speaking, I have the full solution for the eigenvalues. So this is an exact formula. It's not approximate at this point. So these are the exact energy eigenvalues for the full Hamiltonian h naught plus lambda h prime for the two-level system. Now, the second part of the exercise requires you to expand the result of A to second order in lambda, setting then lambda equal to 1, and then to verify that the terms that you obtain in your expansion agree with the results from perturbation theory. So we want to basically do a sanity check related to what we are making to see if it makes sense. So, well, of course, the first order and second order energies. So this is what we have studied so far in perturbation theory. And okay, yeah, of course, you have to assume, Well, we're going to assume that the energies are different. Yeah, so should not have a simple identity case times a constant. And well, we're just going to assume that dB is greater than EA. And okay, if we do that expansion, well, this term is actually quite nice, so we don't need to expand anything. It's the square root of these squares that we need to study and to expand. And so, well, we might rearrange things a little bit. Actually, I mean, notice that here I have a lambda squared, I have another lambda squared. So it might just be simpler if I put the lambda squareds in a single term by completing the square and then having something squared plus a constant term, which is what I'm going to do. But for that, I need to do the expansion of this term square. So I have the square of this, the square of that, plus the double product of lambda b minus ba, b minus ca. So this is coming from the fact that I basically I'm putting a factor of -1 inside, which doesn't change anything because I have things squared. So -1 squared is 1. And then I have, this is partly done because of the assumption of EB greater than EA. So that I have these factors, you see, so that this is positive. And then I have lambda squared, so this is the expansion. And then here I have 4 lambda squared norm BAB squared. And well, so what I want to do is to basically add these two terms, have a single coefficient, and then complete the square, which is what I'm going to do. So notice that that's why when I go from here to here, I have, well, the coefficient taken as a square root, then this is squared. Here is the term that's basically completing the square. And then I have the difference with respect to the other constant term. So you can prove by basically completing squares that whole enchilada over here is equal to this point. Okay, so this is just completing the square at this point. You can do the algebra. Now, why I did this? Well, because I noticed that I have to do an expansion to second order of this function. So first of all, this lets me manage things way easier by having just the lambda concentrated on this part, although it's squared. But second, because I need to have a good control of the powers of lambda, because I need to expand basically this function. This is the only part of the function or the eigenvalues that I need to expand, like this one. I need to expand to second order. And so what I'm going to do is to use a Maclaurin expansion, which is basically Taylor expansion around 0, because that's what I'm caring about right now, second order in lambda. So of course I'm centered around 0. And so for that, I basically would use Taylor series, centered around 0, where I have to compute derivatives and so on and so on. If I were to do that, so you can do the calculation, it looks complicated, but if you actually do step by step the calculation, you'll notice that many of the terms will vanish. So there is some balance inside. And so when you do the calculation, this is basically the term related to order lambda 0. So this is the term related to lambda 1. And this is the term related to lambda squared. So yeah, there's some balance happening in over here. The only thing that I need to expand to second order is basically the square root of this function. I have this sign of approximate because I'm truncating up to order lambda squared, since I was asked for that. And it's important in the assumption, or it's important to remember the assumption that EB is greater than EA. Because, well, I mean, you're basically taking a square root, and so these terms are important in the sign. And this is important in the sense to know that this term is positive. Because at the lowest order, the lambda equal to 0, you have the square root of something that is positive and it needs to remain positive. So it would be catastrophic if you had EA minus EB given the assumption that you have. So this time is taking charge of the lambda 0 order. This is lambda 1 order. This is lambda squared order. So again, if you want, do the calculation to verify, and I'll let you know. I mean, I have done it before. Many of the things balance out, and so that's why you get this cleaner expression, okay? So we're still keeping the lambda at this point. Later on, we'll make it equal to 1. But in any case, so this is the approximation of the eigenvalues up to order lambda squared by doing the expansion for this square root function. So this is approximate. And well, if we want to study the first order approximation of this, we only need to truncate this term because it's the only one related to lambda squared. So we would have to truncate it. And up to second order, we have to keep this power. At the lowest order, of course, we would eliminate lambda terms, which is actually what is happening over here. So let's just by sanity check, right? Okay, up to 0th order, eliminate lambda terms. You have this term over here, plus minus this other term over here. And let's study what the plus and minus terms are about. If I do that, basically I get cancellation. For some terms, some of them add up, and divided by 2, for mu plus, I get E0b. For mu minus, I get E0a. It will be some cancellation. And actually, I need to add a parenthesis in here. Sorry about that. Okay. So yeah, you can see that for the plus case, basically, this adds up, this cancels. That's why the E0a disappears. And the opposite happens for mu minus. Of course, then you have the factor of 2 dividing. And so this defines basically mu plus corresponding to the B level, mu minus corresponding to the A level, right? Which is, I mean, EA is smaller than EB by assumption, again, this assumption. So now let's consider the first order, which means that we only have to truncate this part, okay? So up to first order we have, and then we'll take lambda equal to 1 at the end. So we would only have these other terms in here, which is what we have in this part. So plus minus factoring out. Then, yeah, there's going to be some cancellations happening. If I consider basically only the plus sign and making lambda equal to 1, so I have this term and then plus EB minus EA plus BB minus BAA, right? So if I do that again, the A0A cancels, the BAA cancels, the other terms get basically multiplied by a factor of 2 divided by 2 then. That's why I get E0B plus BBB. And then mu minus has a similar situation in which basically now what will survive are the A terms and the B terms will die. And then the division by 2 takes care of the addition. So that's why mu minus is equal to E0A plus BAA. So this is exactly what first order perturbation theory predicts. Because if you notice, these are the unperturbed energies. So these are the 0 order things. And these are the first order corrections if you remember that the perturbation has these diagonal terms. And what is a diagonal term? It's basically the expectation value of the Hamiltonian in the unperturbed basis. Again, so this is exactly what first order perturbation theory predicts. So the correction in the energies, or the energies, are corrected by the diagonal terms of the perturbation Hamiltonian. And you remember that the first order correction to the energy is the expectation value of the perturbation in the Hamiltonian for the unperturbed state, which is exactly what these diagonal terms represent. So we're nailing it at this point. We need the second order, right? So which means to consider the full case and later on making lambda equal to 1. But okay, we incorporate this term. Notice that I had a factor of 4 and a factor of 2 over here. So if I make the division, that's why I get the 2 in this part. Otherwise, it's the same thing. And I'm going to make lambda equal to 1, okay? Because they told me to, and that's usually the way things happen in time-independent perturbation theory. I'll make a comment at the end of the topic. So okay, let's set lambda equal to 1. So this goes away. Then I have the plus minus. this stuff, and then, well, again, we have made the assumption of EB0 greater than EA0. So I have this term. And now, well, I mean, of course, some of the terms will be almost the same that we had plus this correction, right? Which is coming out from this part. So there is no term balancing it out of the plus minus. So that's why for the plus case, you get the plus BAB squared divided by E0B minus E0A. So the factor of 2 goes after dividing by 2. And for the minus, you get the minus sign. So it would be these same things plus minus this other term. So we just have to understand what they mean, and then we will actually see that we are agreeing with second order correction to the energies coming from perturbation theory. So, okay, let's remember, or well, comparing this with the results of second order time independent perturbation theory, we remember that this predicted that the second order correction to the energies are the sum over all states different to the one that we're caring about of the basically this matrix element term squared for the H prime divided by E0n minus E0m. Now, in our problem, we have only two possible levels, which are A and B. And so in this two-level system, saying that you consider all states different to the one that you care about means just taking the other, right? So basically, this means that the second order correction to the A level is the sum over all states not A, which means taking only the state B for m equal to B. So of psi 0m h prime psi 0a squared divided by E0a minus E0m. So that would be basically pulling out this with B. And in the matrix representation of H prime, these are off-diagonal elements precisely, right? Because you're in the other state. And so this is by definition BAB squared, if you remember what was the form of H prime. So H prime was this matrix. Uh, so this is BAB squared divided by E0A minus E0B, because M is equal to B in this two-level state representation. And if I just basically multiply by 1 with minus minus, so I get minus BAB squared normed divided by the difference between the energy levels E0B minus E0A, where I'm doing this because I know that basically the denominator is positive in this case. And if I do the same for E to B, are the sum of all states not equal to B, which means that M is equal to A, of this matrix element, which is off diagonal for the perturbation squared. So that's why I have norm squared of BAB over here. And here I would have E0B minus E0A because M is equal to A. So I have the things in the fashion that I want. And if you notice or compare, I mean, look. So this is telling you what is the second order correction to the energy level A according to perturbation theory. This is basically the 0th order value of the unperturbed energy plus the first order correction to the energy level A, and then plus the second order correction with the minus sign, just as we expected. And likewise, mu plus is the approximation up to second order of the energy level related to the B level. So 0 order, first order correction, second order correction, just as we predicted. So this is precisely the second order corrections to the energies we obtained above. So this is a truncation of the exact formula by Taylor expansion. This is what perturbation theory predicts, and we get an agreement. So we're on a good track both in the development of time-independent perturbation theory for non-degenerate states and the way we solve this problem. Okay, and of course, where we have made the assumption that the B level of energies is greater than the A level. So the last part is, actually, I think that's what puts the value in this problem, because it starts to pose interesting questions to the student in terms of convergence or when do these corrections make sense. Okay, So the statement of the subproblem says setting BAA equal to 0, so basically the diagonal terms of the perturbation equal to 0, show that the series in B only converges if the norm of the ratio between the off-diagonal element and the difference in the energy levels is less than 1/2. That is interesting, right? So well, actually, let me, how can I say? Okay, let me continue. I will explain more about this in 1 second. So we have to go back to the full exact formula for the eigenvalues of these two levels. So which is over here where we have completed the square. And so let's, okay, follow the assumption where the diagonal terms of the perturbation are 0. So this is only done because it simplifies expression. If these are 0, then the off-diagonal term has to be non-zero, because otherwise we would have the zero matrix and this would be a non-perturbative case. So this would be trivial, right? In fact, we would have no problem. And of course, we're going to keep the assumption that we made, E0b minus E0a greater than 0. So if we do that, okay, this is going to vanish. So that's why it doesn't appear over here. So this other term is also going to vanish. So it won't appear in this case. Also, this term is not going to appear. And so if we only have this, basically lambda is being multiplied by 2 absolute value of BAB, which then, of course, is squared and so on, because this term was 0. So you have it again back, and then you have 4 norm of BAB squared lambda squared, plus this constant term, which simplifies because basically this becomes 0. You're dividing by itself, and so that's why you have E0b minus E0a squared. So all this simplifies. And that's kind of like the reason they're telling you to do that, in order to analyze simplification of the full term. So you have, in this simpler case, the exact formula for the eigenvalues is this. Of course, I mean, precisely because you know that E0b is greater than E0a, and therefore this term being positive, you can take it out of the square root. Of course, you have to divide by it over here, since you had it squared. So that's why basically factorizing appropriately and putting things in terms of a squared power, you have this term, right? So plus minus this energy difference times this term, which is square root, divided by 2. And so the reason this was done is because I want to put it in a nicer fashion, where basically I have Taylor expansion or Maclaurin expansion of 1 plus, say, x to the 1/2, where my x is actually the whole thing squared, right? So just think of this as the argument with the square. So we're going to do a Maclaurin expansion in terms of this term squared. So this is the argument. If you want in your mind, call it x for mu plus minus. And so doing the Maclaurin expansion around 0, of course, because by definition, that's what Maclaurin is. Maclaurin is Taylor around 0. So you have the analytical expansion with the k factorial, then the derivatives for these functions, mu plus minus, and then the argument, where I have simply taken square already, to the kth power. And well, if you were to analyze how this 1 plus x to the 1/2 looks, you basically have some binomial coefficients appearing, although the definition has to be kind of like extended, because you have the power 1/2. So these are the related binomial coefficients. Then you have this term to the kth power, and the binomial coefficients that I'm talking about are defined in this fashion. So binomial coefficient 1/2 k, it's like this. So you have 1/2 minus 1/2 minus 3/2, and you go all the way to 1/2 minus factorized k minus 1 divided by k factorial. And you need an extension for the case k equal to 0, which is defined as 1. So this is basically an exercise in calculus. Taylor expansions, or if you want, say, analytic series, if you are thinking of it in the complex plane. But as you know, any, especially from complex analysis, any analytic series has a convergence radius. So it might not be valid over the whole, say, complex plane. So that's important to figure out. And actually, this is quite relevant to the problem, because in a way, that's what they're asking us for. So we have to find the convergence radius of this series. And so we, finding it, basically we define, or we establish the convergence criteria, which is related to this. You will see it in the end. So there is one convergence test, which is called the ratio test, which is the limit, say, as k goes to infinity, between, say, this term and the previous one, which is what we're doing here. So that's the ratio test. If we compare, say, one term with the previous one as k goes to infinity, we're just thinking of the term k plus 1 versus the term k. So you'll have the ratio of these two coefficients, of these two binomial coefficients. Of course, the division of this to the power k minus 1 by the power k is just going to give you one term like this. So that's why we have this in simplified fashion. Now I have to go back to the definition of these binomial coefficients, where, well, I mean, if you notice, if I go to the case k plus 1, I'll simply have one extra factor, and then by definition of factorial, right? So this is why I'm getting this term related to this part, and then the k plus 1 coming from the difference with the k factorial. If I basically account for the difference between this case for k and the other case for k plus 1. So these are the two terms that survive the division. I have this term. I want to make my life easier, especially because I know that k is going to infinity. So I might as well divide the numerator and denominator by k, because it's going to bring up terms that are going to go to 0 as k goes to infinity. So having done that, that's why I have the 1 over 2k minus 1, 1 over k plus 1. And then I still have this term. When k goes to infinity, this basically becomes 0, this basically becomes 0. So I'll have a minus 1, which doesn't matter because I'm taking norm. So I stay with this term. So this is looking closer to what we want to prove, right? If you remember. So basically, this limit, which we are calling L, defines if the series converges absolutely or if it diverges. That depends. If L is less than 1, it converges absolutely. If L is greater than 1, this diverges. So this is actually defining the convergence radius. So this is very, very close to what we want. If L is equal to 1, the test gives no information. Okay, that is well known. This is actually either in your advanced calculus course or in your complex analysis course, you probably saw this ratio test. Okay, so I'm making use of that background. So to guarantee the convergence, of course, we need this limit to be less than 1, because if we are in the case greater than 1 or equal to 1, it might diverge. So we need to have this, which I'm simply taking a square root of everything because all this is squared, less than 1. So that's why I have 2 norm BAB lambda divided by the energy difference. All these less than 1 by basically taking a square root of 1 as well. And passing some terms on the other side, I get exactly what I want. Well, except for one part. So I pass to the other side, so I have 1/2 greater than the whole this. I have to take lambda equal to 1, because I have been told. Yeah, I mean, they're not making use of lambda in this part. So if you take lambda equal to 1, as we usually do at the end in perturbation theory, we get exactly what I want, which is the norm of the ratio of the off-diagonal term of the perturbation divided by the energy difference is less than 1/2. So, well, on one hand, I get what I was asked to. On the other, this is actually quite important in terms of perturbation theory, and I will tell you why. So there's a note from Griffiths indicating, okay, yeah, in general, perturbation theory is only valid if the matrix elements of the perturbation are small compared to the energy level spacings. So, I mean, this is actually a good interpretation of this, right? Because, okay, this has units of energy. And so this is telling you somehow, well, of course, we had the assumption of BAA, BBB equal to 0, which are the diagonal elements. But this is telling you that basically the size of the perturbation in terms of energies has to be small with respect to the energy difference, because if not, you would fail. So otherwise, as is indicated in Griffiths, the first few terms will give a poor approximation and the series may fail to converge. Um, so this is what I want to explain in a couple things. So the first thing is to interpret this result as perturbation theory is valid as long as the perturbation is small. Small with respect to what, right? So this is giving you a partial answer because although this is for a very specific problem where we have made some extra assumptions, this is actually, it is not even that strong of a condition. It's like a necessary condition. It's not sufficient to guarantee convergence or that you are getting not garbage in your calculation from perturbation theory. This is a necessary condition in general, that basically the perturbation or the perturbation in the energy is small with respect to the energy difference. Otherwise, you cannot guarantee that the perturbation theory corrections that you're doing for the energies are good. I mean, you might be computing something, but it might not be accurate, right? The other part that I want to comment, at least to give a partial comment, and then when I finish the lecture, I will give way more detail into this, is that perturbation theory is actually related to asymptotic approximations. And so in asymptotic approximations, what is crucial is that the size of the perturbation or the perturbation parameter is small, rather than you take the whole terms. And so that is partially why we kind of stop at the second order in a way, because let's put it this way. So what is clear from this condition or the moral of the story is that if the perturbation is not small with respect to the energy differences, basically you're not converging, right? Now, most importantly, because this is kind of a condition for the convergence for the whole series, think about it, right? You're basically considering the series from k equals 0 to infinity. What I would say is that in perturbation theory, it's more important that you take small perturbations, meaning small values of lambda. For example, if you do not make lambda equal to 1, or small values of the perturbation Hamiltonian, which is appearing in this case with respect to the energy differences, rather than taking the whole series. You don't need to go to k to infinity. I mean, it is more important to consider small perturbations that basically making k go to infinity, okay? And so that's why this condition is relevant. Because on one hand, again, I mean, I must tell you this is necessary. It's not a sufficient condition to guarantee that your perturbation theory is somehow converging if you go to k to infinity. Um, well, in this case, for this series, yeah, I mean, but there are cases where you can still have this being satisfied, yet you might get some weird stuff with the perturbation theory. Anyways, my point is that there are stronger conditions that need to be satisfied other than this one, but it's also giving you a measure of how the perturbation has to be small. Has to be small with respect to the energy difference in the energy levels. It also makes sense because, well, the energy is relative in the sense that you can always shift the origin of coordinates for the energy. So it's relevant that you consider the energy level differences, which is actually what is measured in spectroscopy. And then the perturbation has to be small with respect to the differences in energy, right? When you jump from one state to the other. So just keep it in mind, meaning that the perturbation has to be small. It's actually way more crucial than taking the k to infinity. And partially that's why we stop at second order. Um, there are more things that I would like to say. Thing is, many of them are related to basically asymptotic analysis and asymptotic approximation. I will mention at least the gist of it, in fact, and give more references. But keep it in mind, this is giving a measure of how small your perturbation has to be so that basically you're not computing something meaningless, right? So in any case, for the moment, this is what I want to present and what I want you to think about, that there are some conditions so that perturbation theory calculations actually make sense and they're meaningful and you're not computing garbage. Excuse me. Which is well understood in this case where we're posing the problem as some sort of complex analysis, which partially is. But again, it's actually stronger. I mean, it's more meaningful or more important that the perturbation has to be small rather than going to k to infinity. So that's all what I want to mention. So for the moment, this is all related to second order correction to the energies for non-degenerate states. I'll continue with the degenerate case in the next week. And for the moment, I think this is enough. Try to study this. Try to review the calculations by yourself. I mean, they're basically making use of Taylor expansions, and you just have to be patient and do things step by step. But there is quite a reduction happening in some of the terms. But I want you to give the gist of what you need, right? And we basically used Taylor expansions and convergence criteria for complex functions, and this is how we got the result. Okay, so hopefully this will be helpful. I wish you good luck with the remaining part of the homework. And again, if you have any question, I'm available during office hours on Tuesdays and Thursdays from 1:45 to 3 p.m. And I'll be happy to meet with you and help you. So good luck and hope you like the class.